Hello, and welcome to this webinar presented by Flexible Circuit Technologies. My name is Matthew, and I'll be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The windows with the heading Presentation are the primary windows for today's event. On the right side of the screen is the Speaker Bio window with background information on today's presenters. On the bottom left of the screen is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now I would like to introduce today's presenters. With us today we have Carrie Burkett, FCT's Vice President, and we also have Mark Finstead, FCT's Director of Application Engineering. To read more about our presenters, please look at the Speaker Bio window right next to the main presentation window. And guys, welcome to today's event. And with that, I will pass things along to you to get started.
Thank you, Matt. And also appreciate the introductions of Mark and myself. And then for today, I wanted to review the agenda with you. We're going to do a quick view of FCT and then get into our webinar on why use Flex, mechanical electrical considerations, cost drivers, and then question and answer sessions. So I'd like to thank all of you for joining today, and we look forward to going through our webinar with you. First of all, just a quick view into FCT. We're a premier global supplier of flex circuits, rigid flex, flexible heaters, membrane switches, plastic moldings. We offer superior flex design services and then value-added EMS assembly to product module all the way to complete product box builds. One of the things unique about us is our business model. We're headquartered in the Minneapolis, Minnesota area in the USA, where we have our superior design services, senior engineers that help our customers get to cost-effective designs that will perform. We also do all of our program management, customer care, customer support, and coordinate activities with our customers out of this location. And then we have Asia-based production facilities that focus on building high-quality products and getting them shipped on time to meet our customers' needs. This leads to a very cost-effective approach and business model in support of our customers. The other thing is our model allows us to offer nearly 24-hour support. We're USA by day, and then our Asia teams are working by night. So it works out really well. And again, we have customers all across the globe. From a product standpoint and service standpoint at the highest level, single-sided flex, double-sided flex, multi-layer, flexible heaters. We do large format circuits as well. So you see a listing here. EMS services. This is what we have in our FCT Shenzhen, our main hub in China, with the 9 full SMT lines, clean rooms, electrical workshops, and more. We have outstanding capability in the assembly area. I mentioned we do product module builds and then all the way to complete product builds. Often that's in medical, and we actually build a lot of medical FDA products or registered product programs as well. From a service standpoint, superior design consultation and design optimization. This is one of the things that really sets us apart in bringing just very talented and experienced engineers to our customers. We also provide technical leadership in our industry with IPC. Mark is actually the vice chair over all the IPC Flex Circuit committees. We're also one of the leading educators on flex circuits at IPC sponsored events, and also direct with our customers when they have interest. We do prototyping and then small to very large scale production, component procurement. We'll help manage all that, testing services, inventory stocking programs, and attentive overall program management and account team assignment. From an industry standpoint, we focus on commercial markets. So our top markets would be medical, automotive, consumer, industrial, telecom, data. We also support globally and regional EMS and CMs, and then also help and work with a lot of product development labs. This gives you an idea of our locations, Minneapolis being the main headquarters. We have technical sales support in Europe. And then Shenzhen's our main hub in China, where we have our management team, production program managers, and our assembly facility. And then we have 3 Bearflex facilities in Zhuhai, Zhangzhou, China, and Xiamen, China. Zhuhai being our newest 485,000 square foot facility with the latest state-of-the-art equipment. And then Huizhou, China is where we're opening up and did in January our new EMS assembly facility. That's an 800,000 square foot facility that we're very excited about. We also have a plastic molding facility. And then in Korea, we have certified production partners. We tend to go there when we have requirements that maybe are outside of what we can do in China or specialty needs, if you will. Certifications, probably the main ones I would point to is 13485, 16949, and then we've also passed numerous 6.3 audits, which is basically European automotive, more stringent than 16949. So we do have excellent quality systems in place that allow us to deliver high quality products for our customer. Beyond that, experts in addressing industry trends. One of the interesting things in this industry is that flex circuits, rigid flex, flexible heaters, these specialty interconnects have really been growing at a rapid pace. And it has to do with the trends, miniaturization and Internet of Things, mobility, wearables, data collection and connectivity. Just all those things have driven the need for these types of products and driven engineers that are doing product development to these types of solutions. At the same time, there really are few experts. I mean, experts that truly understand the materials, the material properties, what can be done, what can't be done. Resources have literally worked with thousands of projects. And that's the difference in what we bring to the table is our engineers do bring that type and level of expertise. And that's what allows us to help our customers get the cost-effective solutions to do it more quickly and getting you down the product development path more quickly, helping to save money, and again, getting to cost-effective solutions that can be produced at high yields. And that's what we pride ourselves on in support of our customers. This just gives you background of our people. And again, if you have interest and would like to do a more thorough introduction with us, by all means, reach out. Same with our capabilities. I'm not going to go through our capabilities chart today, but if you have interest, we'd be happy to do an introductory call and explore more deeply with each of you. From there, assembly services, as I've mentioned, we do a ton of placement of components, but beyond that, offer the product module, the complete box build services, some specialty areas, hot bar soldering, ACF bonding, 01005 component placement, VGA assembly. So this just gives you some information background on our assembly capabilities. So in summary, what we bring to the table is the renowned engineering expertise. That's probably our biggest differentiator. All of our application engineers here in our Minnesota at headquarters offer above 25 years of design and fab expertise. And that really matters today when you're getting into specialty interconnects. Again, understanding the materials, material properties, what can and can't be done, and getting our customers to cost-effective solutions. From there, our business model is unique, allows for streamlined operations, and again, allows for us to provide quality services, but also cost-effective solutions. Excellent customer service and support is ingrained in our staff here. And then to have the certified facilities with robust quality systems really allows us to perform for our customers. So with that, I thank you for letting me do a quick overview. And I am going to turn it over to Mark as he gets into the educational part of our program. Thank you.
Thanks, Gary. Flexible circuits are used in such a wide variety of applications, everything from aircraft to aerospace, defense and munitions, communications like cell phones, Lots of medical applications, both implantable and non-implantable, like hearing aids and implantable pacers and defibs and implantable pain management devices. We're also seeing a lot of applications in medical diagnostic equipment. There's a general misconception by a lot of people that flexible circuits are used to replace standard rigid PCBs, when in reality, flexible circuits are used to replace wires. The main reason for this is that wires and wire harnesses have to have insulation around each individual conductor, and flexible circuits are able to do that in a much more space-efficient manner. By saving space in an enclosure, it allows increased functionality of different devices and also improved performance and much lighter weight. Because flexible circuits don't have to have insulation around each individual conductor, we can eliminate the mass associated with that insulation. And this can result in 40 to 50% savings in overall mass. And this can really come in handy if you're designing applications for small handheld devices and also for a lot of aerospace applications and munitions where mass is critically important. You can also get much better electrical performance from a flex circuit over a wiring harness. We are able to perfectly match all of our differential pairs lengthwise for optimum performance, and there's no way that you can do that with a wiring harness when the wires have to be individually cut and stripped and soldered. So we can give you a much better and a much more efficient routing than you can get with a wiring harness. Most electrical assemblies, when they do fail, typically will fail at a soldered connection or where a wire is attached or something like that. Flex circuits can give you much higher reliability because everything is on a single connection plane and you don't have all of the individual connections that can be a reliability problem. The Mill Handbook 217 shows that wires are typically good for about 457,000 hours mean time between failures, whereas a flex is good for over 2 million hours between failures. This slide shows the different specifications that you'll be referring to when you do your flexible circuit design. The IPC is the organization that oversees electronics and specifically flexible and rigid printed circuit boards worldwide. Specifications that you'll use during your flex circuit design are IPC 6013, which is the performance specification, and IPC 2223, which is the design specification for flexible circuits. I have 50884 is also listed here. It's a military specification. However, that has been obsolete for new designs for close to 20 years now, so we rarely see that. So the IPC is pretty much all we're seeing for both design and for performance. The materials on your flexible circuit drawing should be called out per the IPC specifications 4202, 4203, and 4204. And like I said, by referencing those on your flexible circuit drawing, you'll make sure that you get the right stack up. Now we're going to look at electrical and mechanical specifications and requirements that will be needed on your flexible circuit design and how each of those requirements can impact other requirements on your design. Flexible circuits are unique in that, unlike a rigid printed circuit board, they have to be able to fulfill all the electrical requirements of the application, but in addition, they have to be able to bend and fold. So there's a whole new suitcase of requirements that are mechanical and physical in nature. And those can really cause an issue because most of the characteristics that will improve the mechanical performance are detrimental to the electrical and vice versa. So when you look at the electrical requirements that's needed on any printed circuit board, whether it's flex or electrical, you've got current requirements, voltage requirements, impedance control, and we're going to go over these one at a time. So we'll start out with current carrying requirements. Obviously, you need your conductors to be able to carry the amount of current required to support your application, and you want low conductor resistance to minimize your voltage drop, and you also want to control your temperature rise because you typically don't want any extra heat being generated in your flexible circuit. This slide shows a conductor with nomograph taken from IPC 2152, and this is also available on our website in our design guide, where you can calculate the amount of cross-sectional area that you need for your traces, and you can get an idea how much heat is going to be generated in a particular trace based on the amount of current and the line width and the copper thickness. In the absence of room temperature superconductors, we're pretty much limited to copper for our traces. And there's only a couple of ways that you can deal with high current applications on a printed circuit board, whether it's flex or rigid flex. And that's either wider conductors or thicker conductors, and you have to increase your cross-sectional area with one of those two features. So if you look at the results of increasing either your cross-sectional area with trace width or trace thickness, you can see that what happens is you're either going to have an overall larger physical size of the circuit because your traces are wider, or you're going to be able to get fewer nets per layer, which may increase your layer count. If you increase the copper thickness, you're also going to have to increase the adhesive thickness so that we can encapsulate around those conductors. And so that's going to give you an overall thicker and stiffer circuit. So basically, by increasing your current carrying capacity, you're also increasing your stiffness. This is an animated cross-section of a ultra-flexible two-layer circuit where you'd be using half-ounce copper with pads-only plating, 1 mil adhesiveless polyimide core, and then a 1 mil polyimide cover top and bottom. You can see the overall thickness is about 6/1000ths of an inch. Now, if your application requires higher current, where you had to go with a thicker copper thickness, you can see here, this is a basically the same type of circuit, 2 layers, but we have 2-ounce finished copper. We started with 1 ounce copper and did a panel plating to get us up to 2 ounce, a 1 mil adhesiveless core that we still have. But you can see on the outer 2 cover layers, we now have 2 mils of adhesive instead of 1 mil of adhesive. So overall, we're now up to a 10 mil overall thickness instead of a 6 mil overall thickness. So we increased our overall thickness by over 40% just by increasing the current capacity of the circuit. And this is an animated of the 2 stacked up side by side showing the scale. You can see there is a significant difference in overall thickness that ends up as the result of the increased current carrying capacity. So to quickly summarize, high current is going to require either wider and or thicker conductors. It's going to require possibly additional layers, making the circuit thicker and stiffer. And thicker foil is going to require additional adhesive to encapsulate the conductors, which is going to make it even more thick and stiff. And what you're going to find is high current applications typically result in a flex that's only suitable for static applications, where it's a flex to install and isn't required to bend and do a lot of additional dynamic movements after it's completed. So now we'll look at the voltage requirements. High insulation resistance and high dielectric strength and breakdown voltage. Fortunately, the materials we use for flexible circuits are really good when it comes to dielectric potential. Polyimide film is good to close to 5,000 volts per mil, and the adhesives are about half that, which is still very good. So you're going to get very good dielectric breakdown and insulation properties from our materials. But in certain applications where you do have high voltage potential, you have to be mindful of these 2 things. The way you would improve them from where they currently are would be to increase your conductor spacing or increase your layer-to-layer spacing to make sure there's nothing short in between layers. The results of that is typically making your overall circuit larger, because you're going to need to space your traces out, and that's going to take up more real estate on each layer. You may then need additional copper layers if you run out of space, and the extra copper layers are now going to work against you because you're going to be making the circuit additionally thicker, stiffer. And you can also increase your dielectric between layers. Again, fortunately, the polyimide films are really good. Typically 1 mil is more than enough, but when more is required, that's going to make the circuit even thicker. Signal integrity is becoming extremely important as switching speeds continue to increase. So we're very concerned about impedance control. We want the minimal amount of signal distortion due to reflections. We also want low crosstalk and low insertion loss to make sure that we have the same signal level at both ends of our signal transmission line. And we also want good isolation and minimal noise that's going to be messing around with our signals. When we're trying to get elevated impedance, there's a few ways we can do that. We usually start by reducing our trace width, and we also can increase the dielectric spacing between our signal and plane layers. We can also use non-standard low-loss materials, which can help elevate our impedance without increasing the thickness. Unfortunately, the results of any of these is going to have an impact. If you use the newer materials that have the low loss but still are flexible, you're going to be paying a premium because they are considerably more expensive than standard materials. Increasing your dielectric spacing or your signal plane spacing is going to increase your overall thickness, and reducing your trace width is going to have an impact on both yields and on the reliability of the circuit when you bend it. So to illustrate the impact of elevated impedance requirements on a flex circuit, let's go back to that original very flexible two-layer design that we talked about earlier at 6 mils overall thickness. If all you're looking for is impedance matching, you can go with a microstrip type construction, which would only increase the overall thickness by about 0.02 of an inch. So it's not going to be a significant amount of circuit increase. However, one of those layers is going to be solid copper, so it will get a little bit stiffer, but it won't have a huge impact. So here you see a comparison of the two stack-ups with the standard two-layer without any impedance requirements versus the two-layer microstrip requirements. And this is, you have to keep in mind that this is microstrips, so this is only good if you're looking for impedance control only. If you're looking for isolation, you're going to have to go with strip line construction, which is going to have a much bigger impact. But you can see that even going with just the microstrip application, there is going to be a noticeable difference in overall thickness and therefore a little bit stiffer. If your application requires both isolation and impedance control, you are going to be driven to a strip line construction. And that's where you have two plane layers for your outer layers and a signal trace layer in the middle. So you're now up to 3 layers. You also have to space those layers out because you do get considerably more capacitive coupling between your internal layers and your plane layers. And in order to get the elevated impedance, they really have to be spread apart. And so here you can see if you needed a 100 ohm differential using standard materials, you're up to over 20 thousandths of an inch. So you are almost three plus times the thickness of a standard 2-layer circuit and 2.5 times the thickness of a strip line or a microstrip construction. So going to a strip line construction can have a very major impact on the stiffness of the circuit. So if your application has elevated impedance, anything over 50 ohms, it's almost always going to require that you do have a thicker dielectric to space your signal and return paths out. You're also going to need at least 1 shield layer, in many cases 2 shield layers, and those shield or plane layers are often solid copper, which is going to significantly increase the overall stiffness of the circuit. One trick is you can use crosshatch planes. You don't see this very often in rigid boards because flexibility isn't an issue, but in flex you can crosshatch the planes. By crosshatching a plane, you can see that you have reduced the amount of area that's going to be adjacent to your signals, and by doing that you can actually put them closer together and still get the elevated impedance. We typically like to have our crosshatch running 45 degrees to the length of the signal traces to make them as uniform as possible. Another trick is to use a shielding film like Tatsuda material or silver epoxy, which are both of these are much more flexible than a solid copper layer would be, but they can potentially have a difference versus copper if you're using them as a return path. So you're going to want to do some testing on that to make sure that they do perform the way you want them to. But from an isolation standpoint, just EMI, they are both very good at keeping the circuit running quiet. Here is a cross section showing a standard 3-layer circuit where you can see 2 copper layers. This would be a strip line construction, and this would be the same to scale cross section using the Tatsuda material. Those shielding films are less than 1 mil thick, so they add very little to the overall thickness of the circuit and have almost no impact on the flexibility. So here's the two of them to scale side by side. You can see that it has a huge impact on the overall thickness of the circuit. And the last thing you can do is look at those lower dielectric constant materials, and these will have a significant impact on the cost of the circuit. While they will keep your circuit very flexible and allow you to make it thinner, there will be a premium attached to them cost-wise. You're also going to have to take into account physical requirements in your design that can be things like operating temperature, physical space limitations, and chemical resistance, and see how those will impact the overall package and design. The application, whether it's static or dynamic, shock and vibration can have an impact. And your operating environment, if you have high temperature requirements, typically the standard thermosetting adhesives we use are not great at higher temperatures. So you'll probably have to go with a different adhesive that laminates and operates at a much higher temperature. This is going to have a definite impact on the stiffness of the circuit because these adhesives are stiffer, and it's also going to have an impact on the overall cost and on your supplier base, because not every supplier has equipment that can laminate those high temp adhesives. If you have physical space limitations, this is pretty much going to force you to have tight bend radiuses and decrease your circuit size and thickness in order to be able to get it into the small area. If you have chemical resistance issues, the only way to really protect your circuit, if it's a very caustic environment, because that's usually the worst thing you can do for a flex. They're very good from an acidic standpoint, but not so great for alkalines. So the way you protect them is to use a Teflon or an LCP or other exotic material that's used as an encapsulant that you would laminate over the top of your existing cover. And this is something that can certainly be done, but there's definitely a cost added to it because some of these materials are extremely expensive and very difficult to work with. And as far as the application, static versus dynamic, when you look at your static applications, are you going to be able to form it the way you want to so that it'll fit? If it's dynamic, it's going to have to be ultra flexible. You're going to have to take into account neutral bend axis and things like that that really don't play nicely with impedance control and other things like that. So those are all going to have to be weighed. If you have high shock and vibration applications, if you have a thicker circuit, it's going to be increased mass and it's going to be much more impacted by any kind of shock or vibration. And combinations of all of these features can certainly come into play and cause issues. So really what you're going to find is flex circuit design is going to be a balancing act. Your electrical and mechanical engineers may not get exactly what they want. Everything has to weigh in and everything has to work. And so you may find that you may not get absolute flawless electrical performance in order to get the mechanical features to work, and vice versa. So really what you have to do is clearly identify in your design what are the crucial electrical and mechanical features that you really need. Ensure that you meet those, and then give some slack on some of the other features so that you can meet all the requirements and make all of them acceptable and get a successful design. Now we're going to get into cost drivers, and pretty much every customer is concerned about cost. It doesn't matter if it's for an inexpensive application like a greeting card or something that's going into an F-35 jet. Everyone's looking to save money wherever they can. So we're going to look at some of the things that can impact the cost of your flexible circuit. Flexible circuits are almost always going to be more expensive than a comparable rigid PCB. If you compare it to a similar rigid PCB of size and layer count, the ultra thin materials that we use are always going to cause the flex circuit to be more expensive. Our materials themselves, just the base materials, can be up to 10x or more expensive than standard rigid board materials. But probably the biggest problem is that those materials are very, very fragile and dimensionally unstable. And because of those two features, it causes our yields to be much lower than a rigid board manufacturer would have. And for that reason, it causes flex circuits to be more expensive. So if you look at what the heavy hitters are, the things that really impact the cost of your circuit, layer count, and this is the same as you'd find on rigid PCB, circuit size, your circuit shape, and your panel requirements also will have an impact. So here's an example of a standard panel. We're going to call this 12 by 24 just for argument's sake. Every manufacturer is going to have probably 2 or 3 different standard panel sizes that they use, and it's important to understand what the manufacturer's panel size is when you're looking at your design. So let's say this is a 12 by 24 panel, and you put a circuit on there and you design a little bit of extra service loop in there, and so when you get done, it's just slightly over the halfway mark. Now, no matter how I panelize this, the best I can do is 4 parts per panel. Now, ultimately, you're going to be buying that entire panel. You're going to get the circuits, and you're also going to be paying for the scrap that goes in the garbage. So you really would like to have as much of that circuit being shipped out in plastic bags as finished product, and as little as possible going in the garbage as scrap. So in this particular case, if that service loop could have been made just a little bit shorter so that you could fit it just under the halfway mark, we can now suddenly get 8 parts per panel. The panel on the right, those parts are going to be roughly half the cost of the parts on the left, even though we only decreased the overall length by maybe 1/4 of an inch. So it's very important to be aware of how your parts will fit onto the manufacturing panel. Here's another example. If you had a little arm that was coming out, you can see that that arm is reducing your panel density by 25%, which is going to be just about a direct correlation to a 25% increase in the overall cost of that circuit. So in a case like this, you may want to look at that tiny little arm and say, you know, it might be better to just have 1 or 2 wires coming off of there rather than having that arm, just from a cost standpoint. Some customers prefer to do their own SMT on the flex circuits, and in those cases they would like to have them typically supplied in pallet form so that they can process them through their SMT equipment. Many times what we see happen though is that the requirements for the pallet size and the circuit size end up wasting a lot of material, and this can have a huge impact on the cost. If you look at the current slide here, you can see that the parts are spaced a long ways apart, and there's an awful lot of scrap that would be generated with this layout. You can see all of the dead space that you do not want to have on your panel, because that's all going to go into the scrap barrel when it's all done and ends up being amortized into the cost of the circuits. This particular one could have been repalletized, where you increase your material by about 50%, but you're getting 3 times as many parts on a panel. So this would have a huge impact on the cost of the circuits. They're going to be a lot less expensive because you're not wasting nearly as much material. Another huge cost driver that we see is when a customer has unreasonable X-out requirements. They would like to have their circuits shipped in pallet form, and let's say you have 15 or 20 parts on a pallet, and they require that there's no X-outs. Now that's going to have a huge impact, because if I have a pallet that has 1 reject on it, I have to throw that entire pallet away, which means I'm throwing out 19 good circuits because there's 1 bad one on there. And so that can have a huge impact, because the cost of all those good circuits going into the scrap barrel is going to be amortized out over the ones that are shipped. So you want to make sure that you do have reasonable X-out requirements, and almost all modern pick and place equipment is capable of skipping over reject parts very easily, so you don't have to populate them. So there's really no reason that you should have unreasonable X-out requirements. The typical is 20 to 30% X-out requirements. That gives you the most efficient use of the space, and you don't throw away a lot of good parts. Circuit type can also have an impact on the cost. I'm talking about a multi-layer flex versus a rigid flex. Here you can see the difference between the two. The upper left is your multi-layer flex, where it's pure flex material. The lower right one is a rigid flex, where you actually have rigid material laminated top and bottom, and you have electrical connection going all the way through it. Those top and bottom FR4 or polyimide layers are not just stiffeners. They're not just mechanical stiffeners. There actually is electrical active circuitry on them. So these two are both very, very common, but the upper left design will be a lot less expensive than the lower right one will. Here's an example of a rigid flex design. You can see you have SMT on the rigid area, and then the flex tail coming out. Here's a similar application where you have SMT, but it's only on one side. When you only have it on one side, one of the tricks is to use a multi-layer with a stiffener. And the stiffener is just a mechanical support that we put on the back side. And this is going to be a much less expensive way of doing it than a rigid flex. The only drawback is all of your SMT has to be on one side in each area that you're doing SMT. So in this particular case, all of the SMT was on the top side, which is shown on the left, and the stiffener is on the back side, which is shown on the right. Feature sizes can also have an impact on the cost of your circuit because they can impact our yields. Small pads have to be stacked up on multiple layers, so that can have an impact. Your traces and spaces, as they shrink down to 75 microns or below, definitely the yields will be impacted, and parts that end up going in the scrap barrel versus being shipped out, the cost of those parts get amortized in, so they can have an impact on the overall cost of the finished parts. Here's an example. If you had, let's say, we'll call this a 12 mil pad, and you now have to stack up 4 layers of these. And so let's say that you're off by just a couple of mils on your registration from layer to layer as you start putting those different layers on there. At some point, you have to be able to put a via in there that goes all the way through and connects everything together. So where do you drill where you can have annual ring on all the different layers? Fortunately, there is a most modern manufacturers have optic drills that will allow you to optimize where that hole is drilled and position it in a place where you will have annual ring on all the different layers. However, as things get smaller, sometimes even the optical drills aren't able to put a hole in a place where there's going to be a pad. Your material type can have an impact on the overall cost of the circuit. Adhesive based versus adhesiveless. The cost is not nearly as much as it used to be. It used to be a significant delta, but now those are pretty close, and so we use adhesiveless on a lot of parts, even though it's not probably as critical. LCP, liquid crystal polymer, that has a huge impact on the cost. The cost of that material can range anywhere from $20 to $50 a square foot, and if you've got 3 or 4 layers of that in your circuit, you can get an idea of how that's going to impact the cost of the circuit. And any other non-standard exotic materials, anything that's not run-of-the-mill, that's made in small quantities, not sold in high volume, is going to be more expensive, and that's going to certainly impact the cost of the circuit. Via types also have a huge impact on the cost of the circuit. Through holes are far and away the least expensive to do because it's one drilling and plating operation. Blind vias will be next in line, followed by buried vias. And one thing to keep in mind is that as you're doing your design, each unique via structure will have a price tag attached to it. So just because you have blind vias, a blind via from 2 to 3 is not the same as a blind via from 3 to 4. Those are 2 separate unique via structures. The more via structures you add, the more sequential laminations that you're going to be requiring the supplier to do, and you can actually increase the number of cycles by anywhere from 4 to 10 times the number of processes, because when you're doing sequential laminations, you're building until you're about 80% complete and then go all the way back to the beginning and run it back through again. And of course, each time you do the cycle, there's going to be fallout and yield. So having many different via structures will have a huge impact on the cost of your circuit. Here's one of my personal favorite cost drivers, and that's an over-dimension drawing. Keep in mind that flexible circuits are flexible, and you do not want to try and dimension them like a machine piece of steel, because they're not going to be able to hold those dimensions. The materials themselves are not dimensionally stable, and they can grow and shrink by up to 1 mil per inch just with temperature and humidity. So if you have a circuit that's, let's say, 20 inches long, and you put a plus or minus 10 thousandths of an inch on the overall length, that could change just with temperature and humidity and basically grow and shrink out of tolerance. You have to keep in mind that any dimension that you put on the drawing, we have to verify. And if we have to verify it, there's going to be a price tag attached to it. So what you need to do is ensure that the only dimensions you have on your drawing are critical dimensions that really matter. It's good to have a couple of overall dimensions so that we can make sure scales are proper. But other than that, if it's not critical, don't put it on the drawing. Let the Gerbers drive the circuit. If you have a multi-layer circuit, having dissimilar layer counts in plated through-hole areas can be a cost driver. I've had a lot of designs over the years where a customer has got a design where there's maybe 6 or 8 layers, and they'll tell me that, well, in this one area I only need layers 2 through 4. Can I save money by not putting layers 1 and 5 through 8 on there? And the answer is it can be built, but you probably will quadruple the cost of the circuit. You want to make sure that your layer count in each area that has plated through holes is exactly the same. Even if you're just putting pads on those layers, don't try and delete them, because that it can be done, but it makes it very, very expensive. A lot of masking is required and a lot of hand operations in order to be able to manufacture that. So make sure that all of your plated through hole areas have the same layer count. If you have a large circuit, it's going to have an impact on the cost up and beyond just the size of the footprint that it's taking up on the processing panel. As I mentioned earlier, manufacturers have standard panel sizes, and if your part does not fit on that standard panel size, it's going to require some significant changes in their processing in order to build a part, and that's going to definitely have an increase on the cost of the circuit. Thick copper can also have an impact on the cost of the circuit. Anything over 2 ounce. While 2 ounce is still fairly common in the United States, you rarely see it in any Asian manufacturing. The most common in Asia is ½ ounce, and in the United States it's 1 ounce and ½ ounce, kind of a 50-50 split there. We're also seeing copper weights migrate closer to 1/3 ounce or even 9 micron in Asia in a lot of cases to be able to define smaller features. On your design, you're going to want to pick one final finish and go with that across the entire circuit. It is possible to have multiple final finishes, having ENIG in one area and solder or something else in another area, but it's a very expensive process to do that. It typically requires that one area is masked while the other area is finished. Then the masking is removed from the first area and a mask is put over the first area that was plated, and a new finish is put on the now unmasked area, and then that is removed. And all this is typically done by hand. So you can imagine the amount of time that it takes for operators to be applying and removing masking tape in these different areas on panels. So you want us to go with one particular finish and stay with it. It's a good idea to contact FCT when you have questions, and we can certainly help guide you on what the best finish is for your application.
Thank you so much for that great presentation. And now let's get to the Q&A. We do have some questions that have already come in from the attendees, so we're going to move into answering those right now. If you haven't submitted your question yet, you can still do so now by adding that information to the Q&A box on your screen and clicking submit. Even if it's just a comment, we would love to hear from you. Now, we're going to try to answer everybody's questions today. However, if we don't get to your question for whatever reason, we will be reaching out to you after the webinar is over. So again, please send your questions. We'd love to hear from you. Okay, now for our first question from the audience. What is the smallest bend radius that the flex can bend to? Mark?
Yeah, that's a very good question. The smallest bend radius is typically driven by the circuit type and the circuit thickness. The thicker the circuit is, the greater that bend radius has to be. And so we typically do is we calculate a bend ratio, which is the ratio of the circuit thickness to the bend radius. And what we recommend in IPC 2223 is for single and double-sided circuits, 10-to-1, and for multi-layer circuits, 20-to-1. And those are just guidelines, and they're not hard set rules. If you find that you are, at those ratios or greater, you're probably safe. If you find that you're starting to drop below that, it doesn't mean that it's not going to work. It just means that you may need to spend some time evaluating your forming methods, and you may want to talk to the manufacturer to find out the best way to form that circuit and how to handle it so you don't have problems.
Excellent. Thank you for that. Thank you for that question. Okay, moving on to our next question from the audience. What components am I able to utilize on a flexible circuit?
Pretty much any component that you can put on a rigid PCB, you can also mount on a flex circuit. We do recommend for pretty much all components that you do have some type of a mechanical rigidizer also incorporated in. For SMT components, you'd want to have a mechanical stiffener, something like FR4 is probably the most common, but we could also use thicker polyimide film for keep the thickness down, but something to rigidize it, because if you bend your flex circuit in areas where you have SMT components, whether it's a connector or other components, you can damage the solder joints. So you want to make something, have some mechanical features in there to keep that from bending. For stiffeners, or for connectors, we typically see FR4 as the main thing that's used. And if it's an SMT connector, the stiffener goes on the backside. If it's a through-hole connector, the stiffener would go on the same side as the component, and then the component leaves would go through the stiffener and then be soldered on the backside of the flex.
Excellent. Thank you for that. And to the audience, we just received a whole bunch of great questions. Thank you so much. Please keep sending them in. As mentioned, we're going to try to answer everybody. But if we don't answer you today, you will get an answer after the webinar is over. So again, send us your questions. And also, while you're thinking of your questions and allowing us a chance to pick the next one, since there's so many great ones in the queue right now, I just want to point out on your screen, we have a resource list with some additional content available for you from the FCT team. And we do encourage you to follow up there. There's some great information. And also on the slide displayed, we have the website address. And we also encourage you to follow up there in the Resource Center. You could also download your design guide. All right, let's get back to the questions. And here's our next one from the audience. Can you add a silver chloride epoxy conductive layer on top of a copper circular pad?
Yes, you can. That's it's usually not silver chloride. It's usually silver epoxy. Silver chloride is typically used for membrane switches where you're putting it directly down onto a polyester substrate. If you're going to be going over polyimides or on copper, we typically use a silver epoxy, and that's something that's been done for many years. So it's a very standard process. We don't see silver used as much for shielding, but when it is, it's very common to have that silver go through the cover and make contact to copper pads or copper conductors below it. So you have continuity through the silver shield. So that is something that's very common and can be done very easily.
Very good. Thank you for that. Okay, moving on to our next question. And this actually came in a couple different times. So to all the folks that asked this, thank you so much. And here's the question. How do I terminate a flexible circuit?
There's a number of different ways. Again, pretty much any connector that you can put onto a rigid PCB, you can also put onto a flex. Again, you're going to want to make sure that you have mechanical support for those connectors, because those can be high strain areas, and you want to make sure that you don't damage your circuit when it's moved around. There also a very common method of terminating flex circuits is a ZIF connector, a zero insertion force connector, and they're very inexpensive, and you basically will eliminate, instead of having two mating connectors, you will have the ZIF connector on your rigid PCB and then just basically a pad pattern on your flex that goes into that connector and then it's clamped down. And they're very reliable. I've seen them used in applications ranging from helicopters to cell phones. So they're very reliable. They're inexpensive, and like I said, you're getting rid of one termination method there. You just have the one connector. One thing that I would caution you on, there's two different types of ZIF connectors out there. There's a single row, which has been in use for about 30 years and is very reliable and tried and true. There's also a dual row ZIF option, and those have been problematic for the industry in general. If you're doing something that's small quantity and you have very skilled operators doing the installation, you shouldn't have a problem. But their allowance, if the flex is not inserted perfectly into the connector when it's clamped down, you can actually damage the conductors. And a lot of times that damage will be just a crack that will not show up until the device is actually out in the field. So it's just something to be aware of when you're doing your design. I prefer to go to the single row if you can use those and stay away from the dual row.
Great, some great insight. Thank you for that. Okay, let's see. We have a little bit over 10 minutes more to go in this Q&A session today. So again, send us your questions. We're going to try to answer everybody. We have some great ones in the queue, so let's get to that right now. And here's our next question from the audience. Is there any consideration in using fine pitch or ultra fine pitch components on flex circuits?
There wouldn't be any additional concerns other than just the fact that if your circuit is fairly large, those fine features are going to be more difficult for us to define than it would be for a rigid PCB manufacturer. So when you have a large circuit, it could affect the yields. We can certainly assemble to assemble those components to flex. We do 01, 005 components all the time, so that's that's about as small as they get, and we don't have any problems with that. So, but on very, very large circuits, the larger the circuit is, the more difficult it is going to be for us to define the small features on the flex itself, so it could have some impact on the yields.
Thank you for that, and thank you very much for that question. Please keep them coming. Okay, moving on to our next question. Can LCP materials be laminated, and how?
Yeah, there's a number of ways you can do that. LCP, if you're going to laminate with LCP as your adhesive, it can be done. Keep in mind that it's a thermoplastic. So each time that you hit the melting temperature, it's going to reflow. The temperature is typically over 300 C to do the lamination. It is a very difficult material to work with. We're seeing less and less use for that just because it is so hard to work with. Typically, if you're using it for its low loss properties, I would definitely look at some of the thermal setting materials that are available from several different manufacturers that give you similar performance, and they're much easier for the manufacturers to use. So I would highly recommend doing that. If you're using the LCP to seal your circuit, I would recommend using Teflon instead, because we can get Teflon that has a treatment on it that allows us to use a thermal setting adhesive to bond it on. So I would try and steer away from LCP whenever possible, because even the manufacturers of the LCP will tell you that it's a real bear to work with. So anything that's difficult to work with typically equals lower yields and therefore higher cost.
Business. We actually have another question related to LCP, so let's slide this in here. And thank you, everybody, for the questions so far. This has been great. And here's our next question. Is the placement of chips on LCP baseboard available?
That I can't answer. It's not something that we ever do.
Thank you for that question. If there's any follow-up, you can send more in. Okay, let's see what's next. Wow, again, we have a lot of great questions coming in. Thank you so much to the audience. Sorry, we're choosing the next one here, but we will get there. Okay, and here it is. Can an impedance-controlled signal be run over a hatched copper plane, and how does that affect the impedance, and does that affect the overall thickness of the flex?
Yeah, that's a great question. I kind of touched on that a little bit during the presentation. Crosshatch shields are used on a regular basis for high-speed signals, and it gives you two benefits. The first benefit is that you're removing some of the copper in that plane, which is going to make it more flexible. The second thing is that by removing the total surface area that is in broadside coupled to that plane, you are reducing the capacitance, and therefore you can actually make your space in between those layers less. And so you're basically getting rid of copper, which helps, and you're getting rid of some of the dielectric space in between the layers, and so you can get the same impedance without going quite so thick. So yes, that is a trick that's being used on a pretty regular basis. There are actually calculators for that. If you have the polar calculator available, they do have a module in there that covers crosshatch shields so that you can determine how much spacing you need between your signals and your planes to get the impedance that you want.
Excellent. Thank you for that. Okay, moving along to our next question. Do you have any recommendation for panelization on flex circuits? And what about the positional tolerances for the step and repeat process? And what are the common sheet sizes in the industry?
Well, we'll start with the common sheet sizes. Material, it depends on where you're getting your material from. Some manufacturers will supply the material in 24 by 36 inch sheets, and a lot of the Asian suppliers will supply it in rolls that are anywhere from 250 to 500 millimeters wide and then continuous length. And so it kind of depends on where your circuit is being manufactured on what those standard panel sizes are. As far as the standard panel sizes, every manufacturer has different panel sizes. In the U.S., I can tell you that 12 by 18 is common, 18 by 24 is common, 12 by 24 is common. With flex circuits, the bigger the panel, the more difficult it is to process them just because the material is so dimensionally unstable. It can grow and shrink by up to 1 mil per inch just with temperature and humidity. So, and what you'll find in Asia is because the material comes in rolls, it's typically much smaller panel sizes. So I would say that in Asia in general, you're probably looking at 250 millimeters wide by anywhere from 200 to 350 millimeters in length would be your standard panel sizes. FCT doesn't have standard panel sizes. We have some tricks we use to optimize the panel size based on the size of the circuit. Problem with using just straight standard panel sizes is a lot of times you'll have circuits that just don't fit on any of your standard panel sizes. And so what happens is you waste a lot of material. So by being able to modify the length of our panels, we can basically just make our panel size fit the circuit layout and optimize the material usage. So I think that answers the question.
Excellent. Great job. And great question. Okay, to the audience, we might go over a couple of minutes from the scheduled duration just so we can answer a few more questions here. These are great questions. We'd love to answer them today if we can. So again, we're going to try to answer as many. We are going to have some left over, so you can expect responses after the webinar is over. We thank you very much for those questions. If you have any more, send them in now. But we're going to try to get to these last few here and then wrap it up. So yeah, if you have any last bits you want to send in, go ahead and do it. If we don't get to it before we close today, again, we will reach out later. All right, here's our next question.
I'd like to add one thing to the last question of the recommendations for panel sizes. Mm-hmm. For the recommendation for panel sizes, your best bet is actually to not panelize it yourself. You know, it's better if we do that on our end because we're going to use the most optimal layout to get as many parts as we possibly can per panel. If you'd like the parts shipped in pallet form, then you should have that discussion with us early on so that we can come to a mutual agreement on what the most optimal panel size is or pallet size that you would be getting those parts in, and that's going to be the most cost effective and make the best use of the material.
Excellent, Mark. Thank you for that extra bit. Okay, looks like we have time for 2 more questions, so let's get to that right now. And here's our second from last question for today. Do you have capabilities to do printed flex circuits in polyester substrates?
We can, but there's not really a good reason to do that. The only reason you'd ever use polyester is to save money, and polyimide will outperform it across the board. And we end up having to pre-make our materials because we don't stock any pre-clad polyester laminates, and the cost for us to do that operation is more than if we just bought a pre-clad polyimide substrate, which is going to give you better performance. So we definitely recommend going with polyimide over polyester.
Excellent, thank you for that. And we're actually I think we have time for a couple more here, so let's slide this one in as well. The question is, flex solder mask or cover lay? What is the best option?
That's a good question. If you are going to be bending your circuit sharply, you need to go with cover lay. Flexible solder mask doesn't mean that it's super flexible. It just means it's a whole lot better than the stuff you put on rigid boards. But it will crack if you bend it too sharply. So if you are going to be bending it sharply, you definitely want to go with cover lay. One thing that we do on a regular basis, if you have SMT components, and it's very difficult for us to make rectangular and square access openings in polyimide cover material. So what we'll do is we use a combination. In the areas where we have your SMT, we'll use solder masks because those areas aren't bending. And the remainder of the circuit, we'll use polyimide covers so that you can go ahead and bend them and get the tightest bend ratio or bend radius that you need there. So that's something you can discuss with us, and we do that all the time. And it's a great hybrid that gives you the best of both worlds.
Excellent. Thank you, everybody, for all those great questions. We do have one more we're going to get to in a moment, but I just want to address a few other questions that came in. There's some questions about whether or not the slides are available for download, the presentation, or you can come back and watch this. Just want everybody to let everybody know that you can come back and watch the replay of this webinar, including the Q&A session that we're in right now. You can use the same link that you used today to access it. So if you want to go ahead and share this with your teams or your colleagues, we do encourage that. And that will be available over the next 90 days on the Global Spec site. And again, you can use the same link you used today to access the replay. Okay, and now here is our last question for today's webinar. How does using a Flex Design expert help me to get an improved solution?
Well, the one thing that an experienced designer will bring to the table is not being able to tell you everything that will work, but I can tell you that after doing something for 20, 30, in my case, over 40 years, you see pretty much everything that won't work. And there's a lot of things that an experienced designer can steer you away from early on in the design to keep you from going down the wrong path. And if you rule out all the things that don't work, usually what's left is you have a much better chance of success. So we always recommend in any of these seminars that we do, I highly recommend that if you have a question, give us a call. We're more than happy to pick up the phone and discuss it. And we want all Flex designs to be successful, whether it's us building them or someone else, because it just makes the industry continue to move forward.
Absolutely. What a great answer. What a great question. All right, and that was our last question. So we are going to wrap things up there. Once again, Mark, Carrie, FCT team, thank you so much for the great presentation, sharing all the great insight during our Q&A session today. And of course, we'd like to thank our audience members for being part of this webinar event. As mentioned, you will be receiving an email from us with a link to the on-demand version of this presentation, so you can come back and watch this again or share it with your team. And lastly, if you could, please take a moment to complete a survey, which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.